Hi everyone, I'm Xeno. This is a joint work that I'm presenting today, joint with Trammell Hudson and Corey Kallenberg. So I'll be playing the part, a little lower I think. I'll be playing the part of Trammell and Corey. So I'm going to do the about us for Trammell, even though he's not here. So Trammell, previously it did the ThunderStrike 1 talk in December of this last year. He's more commonly known for his work on the Magic Lantern custom firmware for Canon cameras, but he also sort of digs into old school stuff, and he found the Easter egg picture of the Mac developer team in the old Macs. And so Trammell originally got into Mac work because his company, Two Sigma Investments, it's a hedge fund in New York, and they were looking to start rolling out MacBooks within their enterprise, but they knew of the previous work that had been done by Snare back in 2012, where he said, there's ways to bootkit Macs by using Thunderbolt adapters, and they wanted to see and understand, is this still applicable to the Macs? So they looked into that before going in that direction. Corey and I we've been working for the past couple of years at the firmware level at our previous employer, MITRE, and then most recently we started Legbacor this past January. And we say we do digital voodoo because we basically focus on the deep dark, the black magic, because if you don't know how firmware works, it's just black magic to you. You have no hope to possibly defend against an attacker who's coming at you at this level. So we focus on main PC security as well as all the PC firmware peripherals. So how this collaboration came about is that this past year at CCC, Corey and Rafal Wojciech from Bromium were presenting a couple of different vulnerabilities that we had discovered down at the firmware level. And Trammell was also presenting his ThunderStrike 1 presentation at the same conference. And he basically said, wouldn't it be interesting if we took this existing attack where we use Thunderbolts and we use physical level attacks, and wouldn't it be interesting if we combined them, because these quote PC attacks that we had found and shown on PCs, they're firmware level attacks, right? And it's just a question, does the firmware on the Mac look like firmware on PCs? And if so, can we combine the two? So our primary thing that we want to keep emphasizing in this talk is that UEFI vulnerabilities, the things at the lowest level of the system, at your BIOS level, they're very often shared between many different systems because there's just sort of a common ecosystem. There's code that trickles down from UEFI to other BIOS vendors. So that's our core thesis here. And so whereas normally we would just talk at you for a long time and then end with the sexy demo, we're going to start with the sexy demo today and show you basically what this is all about. So we're starting from a Mac, which someone has gone to grab a Jedi Kitten's screensaver. They've downloaded their screensaver, so we're starting from a social engineering type attack, but there's remote root exploits just as well. We then use this nice Twitter exploit from Stefan Esser, nice little local root escalation that fits in a single tweet. So the attacker escalates to become a root level user. And then now at this point, on some systems, you could just directly break into the flash chip right then and there, right? So it depends on what the system is, what the patch level is, that kind of thing. But so theoretically, on some systems, you become a root level attacker and you can just break into the BIOS right away. And then also, what the root level attacker can potentially do is they can look for Thunderbolt Ethernet adapters that are plugged into the system. And when they find a Thunderbolt Ethernet adapter, they'll update its option ROM. So the PCI option ROM, it's a little blob of code that sits off on the adapter and gets read in by the BIOS as the system reboots. So we can go reflash the option ROM as well. So what that looks like is we put a little sticker on the Thunderbolt Ethernet adapter. This thing is now infected, as is the Mac itself. So we broke into the firmware on the Mac, and we broke into the option ROM firmware on the Thunderbolt Ethernet adapter. At this point, if you reboot your system, take out your little infected thing, keep that off to the side for later. Reboot your system, and now, just to prove that we're there down at the firmware level, you turn on your verbose boot, and now we have a nice little printout at the boot time. It's saying, okay, I'm here down in the BIOS level, and I can subvert anything that runs thereafter, the operating system, all of your applications, everything. But then we wanted to show that this can also spread virally. So we call this a firm worm. It's sort of the first ever sort of instance where someone spreads from firmware to firmware, and not just firmware to firmware, but heterogeneous firmware. So we have this option ROM that exists in the Thunderbolt Ethernet adapter. We plug it into the next machine, and when we reboot the machine, the option ROM gets consumed by the BIOS, and some code gets executed at the BIOS level. And now, again, depending on the system, maybe it can break in directly, maybe it can't. In this case, it can't break in directly, so it hooks the S3 resume script. We'll talk about that later. But you can think of it like I ran some code and I needed to wait until some action happened later on. And once that action happened later on, then I can break into the BIOS. So that's the ThunderStrike printout from the option ROM as opposed to the BIOS itself. And so the thing that we're waiting for later, the particular exploit that we used here, was the Darth Venomous attack, which we'll talk about. Darth Venomous attack gets invoked when you have a system go to sleep. So when you close the lid on your laptop, that's your system going to sleep. We chose to show it here by seeing the fans actually spin down, because when you put your system to sleep, it doesn't immediately go to sleep. It'll wait around for a few seconds. So after 15, 20 seconds, once the thing actually powers down, that's what allows the vulnerability to be invoked, and we'll talk about it later. So once it powers down, it's literally as simple as we powered it down and then we wake it back up. And now, because of that option ROM, it had taken control of some code earlier in the system. And so you close it, put it to sleep, you wake it back up, and now the option ROM level code that was staged and just waiting around, that code is going to get invoked, and that code will now be able to actually break into the flash chip itself. So now that's infected. Right, so wake the system up, and now this is just proving that this particular Mac, we couldn't infect it directly, but we plugged in the option ROM, we booted it, we put it to sleep, we woke it back up, and now we're actually broken in down at the BIOS level. So you reboot the system, and again, there's ThunderStrike 2. It's actually infected the firmware level. And so this was actually a viral spread via the option ROM device, via the little dongle. That little Ethernet adapter there is spreading the malicious software between BIOSes, and then each BIOS can continuously infect every option ROM that it comes in contact with for these Thunderbolt Ethernet adapters. So basically, that's showing sort of the life cycle of this particular firmware. Start with the remote exploit, and it may break into the BIOS directly. It may not. It can break into the option ROM, and then the option ROM can eventually break into the BIOS. And so you keep spreading these, you spread this infected adapter, and the adapter keeps infecting the BIOS of every machine it comes in contact with, and then every machine that it comes in contact with is now infecting every adapter that it comes in contact with. So it's a nice little subversion down at the lowest levels where none of you would ever think to look. And none of you will ever catch it down at that level. So again, the core thesis here is that UEFI vulnerabilities are shared between many different systems, right? So, we want to make it clear, you open up some random ASUS machine. This is an ASUS desktop, and this is a MacBook Air little 11-inch computer. And you wouldn't think that like a tiny ultralight MacBook Air looks anything like an ASUS desktop, but you open them up, their control flow graphs are more or less the same. The only reason this one's a little fatter is because I've got comments over on this side, but overall their control flow graphs are the same. They call the exact functions in the same order, same assembly instructions, the exact same registers. So everybody's machines look more or less similar down at this level, down at the firmware level. So bring it up a level for a second. We got to talk about a little bit about the history of Mac firmware versus PC firmware, EFI versus UEFI. EFI was Intel's original program to try to replace legacy BIOSes. So Intel was trying to make a non-backwards compatible, their x64 architecture, Itanic. So they were trying to say, okay, let's get rid of all this legacy cruft, right? And that's a good thing. That would have been a good thing, right? Had we been able to get rid of all that legacy cruft. But no, it failed in the marketplace. But still, Intel, when they were making the firmware for these x64 devices, they said, let's build something that's more well-structured, more modular, easier to understand, easier to add new components to, so that this will work for us for the next 40 years instead of what we've been using for the last 40 years. So they made this EFI, Extensible Firmware Interface. Apple then, Apple previously used PowerPC Macs, and when Apple moved from PowerPC to x86 processors, they obviously were, tightly integrated with Intel at the time. They said, hey, Intel, we're going to use your stuff. And Intel said, while you're using our stuff, could you please use this EFI framework instead of the old crufty legacy BIOS? They said, sure. And Apple forked EFI version 1 at some point in the early 2000s. Around 2005, Intel tried to get buy-in from the rest of industry, and they created not just EFI, but UEFI, the Unified Extensible Firmware Interface Forum. And they sort of deprecated the old code, and they said, okay, UEFI, we're going to have an open source reference implementation. We're going to go forward with many different vendors from here. Still, there's sort of many, many millions of lines of code that were in common. And so you can have a situation where, some of the vulnerabilities we'll talk about later today, we saw them, on new systems, and they went all the way back into the original EFI code bases. So generally, the main point here is that we always knew that Apple's firmware sort of forked off from the main EFI code base, and UEFI went and did its own thing. And so there was a question of like, how close does an Apple firmware, EFI, old 1 point something firmware with maybe some additional patches, but how close does an Apple firmware look to all of these other PC firmware? Because we know that when Microsoft pushed Secure Boot for Windows 8, right, they said, Windows 8, you must implement Secure Boot. Secure Boot was specified in UEFI version 2.3.1. So it's like we've got a relatively large amount of divergence, and we know all these modern PCs are going to be running UEFI 2.3.1. Macs are running EFI 1 point something. How close do they actually look to each other? And so that was the fundamental question. But like I said, even the modern EDK2 EFI developers Kit 2 for UEFI 2 stuff, even the modern stuff still has a lot of code that's in common with the original EFI code. So they wrote it once, and they said, okay, that works. If it's not broken, don't fix it. So, code just continues to propagate forward. And, you still have, even though we're trying to get to this new modular architecture, there's still going to be all of these, decades of legacy decisions, things around PCI option ROMs, which were specified, decades prior. There's still elements of legacy support which come in and get included moving forward. So basically, we wanted to, when we wanted to work with Trammell on this, we wanted to look at a variety of other vulnerabilities that we had previously disclosed for PCs, right, generically PCs. We had never bothered to go look at these on Macs before because we worked in environments that, were predominantly Windows environments. And so we were just trying to focus on, for these machines in our environments, are they secure or not? So we considered 5, we'll talk about 5 vulnerabilities today. There's a couple other that I'll mention at the end of the slide deck. But these are the core vulnerabilities we'll talk about today. And the 3 in the middle, the 3 in red, are the specific vulnerabilities which the ThunderStrike 2 proof of concept that we just showed the video for, that those actually use. So the first thing we're going to talk about is Speed Racer. And we wanted to look at this one because we knew that this was a Intel hardware vulnerability, right? So it turns out there's a race condition in the behavior of Intel hardware. One of its protection mechanisms just doesn't work due to hardware race condition. And so we know theoretically this should affect Macs just as well as PCs because it doesn't matter whether it's Mac firmware, it doesn't matter whether it's EFI or UEFI. This is an Intel hardware problem. So just to give you a sense of the basics of how the problem exists, there's this BIOS control register that's in the Intel documentation. And there's 2 bits, and the interaction between these 2 bits is sort of interesting, but this is sort of the core access control, the first order access control. It's one of the oldest access controls, so it goes back a very long ways in the hardware. So there's the BIOS write enable bit, and if you can set this bit equal to 1, then barring any other access control mechanisms, then you can write to the BIOS. So set that equal to 1, and now you can overwrite the flash chip contents. So the way that you control whether or not malicious software can write this bit equal to 1 is that there's a BIOS lock enable bit, And if this bit is set to 1, if you set lock equal to 1, then if someone tries to write this bit equal to 1, if they want to write to the BIOS, it will cause an SMI, a system management interrupt. So that invokes system management mode code, and that code, which was put there by the BIOS, will get to be the core access control mechanism saying, all right, do I want to allow this person to write to the BIOS right now? So what Corey presented back at CCC this past December was this hardware race condition. And the fundamental race condition is that if you have a multi-core, even just a multi-hyper-threaded system, a single core with hyper-threading turned on, you can have one core that's continuously hammering and saying like, set BIOS write enable equal to 1, set BIOS write enable equal to 1, and just continuously hammer on that. And then even though BIOS lock enable is set, and even though there's these SMIs firing off, which, then the SMM handler code should theoretically say, no, you're not allowed, no, you're not allowed, no, you're not allowed. Even though that's going on, it turns out that just, experimentally verifiable, we don't know why at a hardware level this works, but we just know that it works. We can just keep hammering and say write, set write enable, write, set write enable, write, set write enable, write. So you have two threads, one of them's hammering to say I want to write, and the other thread's hammering to say write this value, write this value, write this value. And so sometimes it's the case that you get the thing saying set the write equal to 1, and it does set it to 1, and then the next thing sort of slots in right behind it, and it does actually allow the write to the flash chip. So basically that's a fundamental hardware race condition. We disclosed this to Intel back in May of 2014, and then it was first publicly disclosed at CCC this past year. So Intel basically said, the solution for this problem, they said, well, yes, we know that kind of this BIOS lock enable kind of deprecated. They didn't officially ever say anywhere that like this is deprecated, but what they told us is that, we've always been recommending that BIOS makers make use of this latest protection that we've added into the hardware, which is called SMM BWP. It basically says it's sort of an override on this behavior, this BIOS lock enable. It says, I don't even care if someone can set BIOS write enable equal to 1. You can go ahead and set BIOS write enable equal to 1 all day. You must now be in system management mode before I will allow you to write to the BIOS. So this overrides it and says, okay, no longer can my kernel driver just keep hammering on these access control bits. You must break into SMM before you're allowed to break into the BIOS. That's basically what Intel recommends. And so this is kind of how we would look at, a properly configured system. You've got your BIOS flash chip down here. You've got some OS resident attacker. And then in a fully locked down system, the OS resident attacker cannot write to the BIOS because there's first order, this BIOS lock enable. And that's fine, except we know that in practice, this can always be bypassed by Speed Racer. But then there's this second order SMM BWP bit. So when this is set, no one can write to the flash chip unless they're in SMM. And then there's this second order protections called protected range registers, which the BIOS maker can cover some slices of the BIOS and make it so that even SMM cannot break into the BIOS on the regions that are covered by that. So, like I said, we wanted to look at this because we knew this is a fundamental hardware issue. This is not a Mac issue, not a PC issue. It's an Intel issue. So this is, we liked to disclose through CERT because CERT has these nice charts where they say, here are the vendors which said they were affected, here's the ones who said they were not affected, and here are the vendors who said nothing, right? So there's plenty of vendors where CERT will go off and say, dear vendor, these people told us that there's a vulnerability. Are you vulnerable to it? And some vendors just never say anything back, right? So you can pretty much guarantee that vendors that don't say anything, probably vulnerable. Vendors that say they're not affected, maybe not vulnerable, maybe they are vulnerable. So in this particular case, for the purpose of this talk, we wanted to go look at a bunch of different things because we had never looked at them on Apple's system before. But as you noted, Apple said not vulnerable. So we go and we look at the BIOS control register on Mac system. And the literal bit value is 8, which means that, first of all, bit 1 is not set, BIOS lock enable is not set, and bit 5 is not set. Visualize it in your brain, right? You got your 8. So bit 5 is not set, and so SMM BWP is not set either, right? So What this means is that Apple is not using BIOS control, BIOS lock enable bit, or BIOS control SMM BWP. So now here's the point where I say, technically Apple is not vulnerable to Speed Racer because Speed Racer is a mechanism to defeat BIOS lock enable. They're not vulnerable because they're not using the access control mechanism. There's no need to get around an access control mechanism that isn't even there in the first place. So this is what, an Apple system would look like, right? You don't need to bypass this because everything is just straight open. So then there's, this question of there's these gaps in the protected range registers. There's these gaps, one of which is for EFI variables, and another of which, we don't know what it's for. Now, most of the time on PC systems, they will look, similar to this. You go look at the controls on your PC. It may look like this. It may or may not have these upper level protections, but they will generally have protected range registers covering code and stuff, but not covering the EFI variables, because there's an expectation that generally SMM must be allowed to write to the EFI variables. Right? So on most PCs, if we smash all of the EFI variables, it'll just brick the system. So go ahead, try on your machines. If you corrupt all of that space between the gaps, your system will not boot. Now on the Mac, this didn't work. So I tried this on this Mac Mini system, and I overrode all the variables with X's, and it still booted. And I was like, that's interesting. Well, what about this other gap right here, right? So if I smash all of that, and I don't even know what that is at this point, and I still don't know what that is, because I don't care what that is. It's a gap where anyone can write, and so I'm going to write there, and I'm going to see what happens. If I smash that, then the system would actually not boot anymore. And there's a video online which you can go and watch that, but it's not super interesting in terms of demo videos to see a system that will not boot anymore, right? It's just, it's a little bit interesting. You see the fans spin up, so the fans do spin, but then they spin down, and then they spin up, and then they spin down. So you can go watch that on your own time. So the Apple fix for this came out recently in 10.11. They said, an issue existed where address covered by the protection range registers. This issue is fixed by changing the protected range, right? So essentially what they did was this, right? They just covered more of the protected range, but still, there's no sort of mediation from an OS level attacker on the rest of, on these EFI variables. SMM is sort of not in play, not in the picture, and so anyone can write to any of the variables. That may or may not matter. What I can say is that, Apple has a tool at the command line, NVRAM tool. NVRAM tool will not let you change any variable, but given the fact that there's just a gap in here, you can manually change any variable that you'd like. So next vulnerability to consider is this Darth Venomous vulnerability. Sometimes you'll see people misrefer to this as the Dark Jedi attack, but this was named by Rafal Wojcik because it was analogous to what's going on. So this vulnerability has to do with, you saw in the demo video, I put my machine to sleep and I wake it back up, and now I've got a vulnerable system that I can break into the BIOS. So in Star Wars mythos, Darth Plagueis defeated Darth Venomous, and he killed him, and then he would put him into a coma, he'd resurrect him, he'd kill him again, put him into a coma again, and he would continuously wake him and sleep him in order to study midichlorians, in order to study the balance between life and death, in order to enhance his power of the dark side. So the Darth Venomous vulnerability is very similar. Basically, we have a situation where these sort of access control bits that I was telling you about, like BIOS lock enable, there's a situation where they say, when you set this bit, it's locked and it can't be reset. No one can set BIOS lock enable equal to 0. You can't just turn the lock back off, because otherwise that would be pointless to have a lock in the first place. These bits only are supposed to reset when the computer reboots, right? So you reboot the machine, the system goes unprotected, and now you can write to the BIOS if you need to do a BIOS update. But it turned out when we stumbled upon this accidentally with a different vulnerability that I'll talk about next. But it turns out that if you put the system to sleep, because the system in sleep is losing power, right? You're trying to power down as much of the hardware as possible while still keeping the RAM refreshed, for instance, so that you can just wake up quickly. When you go into this low power mode, you are losing configuration for a bunch of hardware. And then EFI and UEFI have a mechanism for you to regain the configuration as quick as possible when you wake back up using a mechanism called the S3 boot script, which we'll talk about next. So this vulnerability was disclosed to CERT back in September 2014 and publicly disclosed at CCC last year. So this is just to give you sort of a sense of what's going on with the boot script vulnerability. Obviously, it's, I can't talk about a half-an-hour talk in 3 minutes, but the basic idea is that your normal boot takes a certain amount of time. It's, too damn slow, right? Why does it take so long to boot? So you boot up your system normally, and what's happening is that the system will actually save off little bits of configuration information into what's called the S3 boot script. This boot script is, per the name, it's a script. It's a script that's going to be interpreted later, and that boot script will be used to sort of reconfigure all the hardware bits by just doing whatever actions are called for in the script. Write this value to memory there. Send that value out of port IO over there. Set this PCI configuration address space to that. So there's basically a bunch of different opcodes that go into the script. And there's going to be, when you wake up from a sleep, when you wake from a sleep, it's going to go find this script, which is going to be located in memory somewhere, and that becomes the fundamental vulnerability. It's just sitting around in memory where anyone can tamper with it. And the reason it's sitting around in memory is because you go back to this earliest specification and they recommended just put it in memory somewhere. So when you're resuming your system from sleep, literally there's a chunk of the BIOS that just goes down the line, and instead of doing everything like you would do in a normal boot, it just executes these various opcodes. But the most interesting opcode is the one sort of at the bottom there, dispatch opcode. This is a nice little catch-all, whereas these are very specific, like write some particular value to port IO or write some particular value to some particular memory address. Dispatch opcode is your catch-all, do anything generically. Dispatch opcode literally just tells the boot script, jump to this address and execute that code right there. So what we have is a situation where we go to sleep and we know that we're losing our lock bits on our BIOS access control mechanisms. We wake back up and there's just some script somewhere in RAM that any attacker can just fiddle with, and they can literally just insert a jump instruction at the beginning of the script that says, I know you haven't locked down the BIOS yet, but I want you to jump over here and execute my shellcode. That's the Darth Anonymous vulnerability in a nutshell. So, if you only knew the power of the dark side, protected range registers, these last access control mechanism and the only access control mechanism which Apple is using, they go away when you go to sleep and you wake back up, right? And now we can use our Force Lightning to attack the code and stuff. So in this case, again, we looked at the CERT disclosures and we said, what did Apple say? Did Apple say they were vulnerable or not? And this one was a little weird because normally we have affected, not affected, and didn't respond. In this particular case, there were only affecteds, and we checked in with CERT on this, and it turned out there was some snafu in their communications. It turned out they didn't actually ever tell Apple. But that's why it's nice that we had our little backup. We also disclosed this vulnerability through the newly formed UEFI security response team. So because we'd been finding so many vulnerabilities and other people had been finding so many vulnerabilities at UEFI level over the past couple of years, UEFI Forum did a good proactive thing, and they said, we've got these hundreds of companies. It's not just your main big, software, big hardware makers, your big OEMs. It's not just those guys who are using UEFI. There's a whole bunch of little guys that are using it as well. So they made a new team called the USRT, UEFI Security Response Team, where you can pass vulnerability information into them, and they will then sort of distribute it out to the other vendors. And given that Apple is a board-level member of the UEFI forum, you would expect them to be processing USRT information. So Darth Anonymous is nice because whereas Trammell's original ThunderStrike 1 attack required physical presence and physically plugging in that Ethernet adapter, Darth Anonymous is fundamentally a remotable attack, right? If you get under the box, you've got a remote shell, you've got your Metasploit shell on the system, you manipulate the boot script in memory, you set it to sleep, and then you set a timer to wake it up immediately thereafter, and now you've got an unlocked BIOS and you can just write to it. So physical access, whether through physical programmers or physical dongles is no longer necessary. So I think, again, this is one of those, bad on the presenter for giving you tiny text that you can't read, but this is just showing the basic process here. So we've got, check what our flash lockdown bits are, check what our protected range registers are up front. Then we're going to manipulate the boot script in memory, so change the entry point to jump into our shell code. Go look at our location. Here's our particular shellcode bytes. It does a very simple thing, which is literally just, as the system's coming back up, normally it would lock itself. It would configure everything, make it locked, and then say, okay, no one's allowed to touch this anymore. We just leave it unlocked, and then we say, lock it, and no one's allowed to touch this anymore. Right? So just lock it into a vulnerable state as it's resuming. At that point, then you sort of, previous step, PM set sleep now, little command line thing to say go to sleep, and then you wake it back up. And you can see then upon wake, all of the protected range registers are gone, so we can now write anywhere in the BIOS. And so we just wrote some hello world to some location that we knew wouldn't break it. So that was the Darth Anonymous vulnerability. It took all of a couple hours in order to install Windows on a Mac, use our existing Windows proof of concepts, and determine that, yes, Macs are vulnerable to Darth Anonymous. Now, there was a very interesting thing that showed up in about the same time frame earlier this spring. The Prince Harming attack, which was named by Katie Moe because Pedro Valaca didn't want to name it, but it's good to have names because they're easier to remember than numbers. I don't care if you don't like Heartbleed and all that. It's easier to remember names. So this is a vulnerability that we had actually seen on PCs back in 2013, and we had been fighting with CERT to get them to release the CERT vulnerability. They basically had said back in 2013, oh, it's patched already on the vendors that you told us about, so we're not going to disclose it publicly because it's already patched. Who cares? We don't need coordination. We're like, no, your job is to tell people that there are vulnerabilities. Anyways, so what happened was Pedro was sort of looking at the same sort of attacks that we had presented previously, and he had seen the title of this talk, and he had seen, correctly inferred, if you have ThunderStrike 2, Sith Strike, it probably has something to do with Sith, Star Wars, Darth Anonymous, right? So he had been playing with the Darth Anonymous attack because another researcher had put out a proof of concept for that. And what he found was that there was basically something that was even worse than Darth Anonymous. There was a very screwed up suspend resumed implementation where basically if you put the thing to sleep, you didn't have to do anything special. You didn't have to manipulate the boot script. You didn't have to do anything. You put it to sleep, and you woke your Mac back up, and it just lost the access controls, and it never reset them, right? So that was a very simple kind of thing. And Pedro had sort of assumed that while we were talking with Apple about these other vulnerabilities that we had told them about this, and that was not the case. So essentially his blog post was accidentally zero-daying a firmware level vulnerability. It's like, dear everyone in the world, you can attack Macs by just putting them to sleep, waking back up, and now you can write to the flash chip. So Apple's response for this was to release EFI Security Update 2015-01. I think that was around June 30th of this year. And we went and we parsed out the results of that, and it was however many, 24 updates. And it essentially meant everything since 2011, potentially has one of these two vulnerabilities. And if you went and looked at the actual changes that were made by this, what they did was they set these protected range registers and the lockdown bit, which stops you from changing the protected range registers. They set that before they ever got to the point where they interpret the boot script, right? So you go to sleep, you wake back up, it's executing some BIOS code, the BIOS code gets to the script and it starts interpreting it. Instead, they set the locks before it interprets the script, so now it's actually in the BIOS where we can't manipulate the locks. So that's good, that sets the protected range registers. But they actually didn't set TSEG-MB, just some other access control mechanism for SMRAM, which was interesting because the original proof of concept that was shown at CCC specifically would unlock this TSEG-MB and then break their way into SMRAM. Our theory on why they didn't lock this is because generally if you look at Apple's architecture, they try to use system management mode as little as possible. Another miscellaneous observation that Trammell had is he bought like the latest and greatest MacBook C that was available when we were working on this. And on that system, he wiped out the entire boot script. He went to sleep, and he was able to successfully wake back up. And that meant that essentially that boot script was not actually being used. So that means that Apple was somehow protecting the boot script on the latest and greatest using some completely different means, which we still don't know. And they hadn't actually backported that and used that protection on the older systems. But what we've heard from Apple on the now latest and greatest, the iMacs that were released a couple days ago, is that the 27-inch iMac, which just came out like 2 days ago, or 1 day ago, I guess, they're starting to use the SMM lockbox, which is essentially Intel's recommended protection mechanism. It's the mechanism that's in the open source reference implementation. It puts the boot script up in SMM where no one can touch it unless they break into SMM first. So, case study 4, option ROMs. So, this is super old IBM PC. And back at these earliest systems, you had your Intel 8088 chip, you had your BIOS, and then option ROMs, which literally were optional ROMs that could be slotted in there. Now, of course, today, option ROMs are not actually ROMs. They're EEPROMs. They're things that are updatable. Otherwise, we wouldn't have been able to just show that ThunderStrike attack. So option ROMs were first talked about as an attack vector in 2007 by John Heisman. But he sort of didn't do much with it. He just said, like, hey, architecturally, this could be a problem. People could put code on these option ROMs and run it in the BIOS. But the important one was here, Snare in 2012, where he started attacking Macs using option ROMs, and he showed how, look, this is code that runs in the context of the BIOS well before the bootloader, well before the operating system, and we know, just from bootkits and general rootkit MO, the earlier you run your code, the more code thereafter that you can subvert and attack and turn off security and all that good stuff. So basically, option ROMs in the UEFI forum, they continuously were going forward. When they started implementing code signing in preparation for secure boot and that kind of thing, they basically said in UEFI 2.3 that option ROMs are a potential security threat. We need to require that we're not going to load them in a BIOS if security is turned on, unless they're actually digitally signed. So because Apple never went to UEFI 2.3 point whatever, they're still sort of on this forked version of 1.1. They're still sort of running option ROMs unconditionally, and that was despite the fact that people had been talking about it for many years now. And this is the kind of thing where it was architecturally fixed in UEFI Secure Boot by using digital signatures, but it's the kind of thing which just requires an architectural fix to secure. And this is just showing that back in Trammell's original ThunderStrike talk, he was talking about what are the bad things that a bootkit could do from the option ROM level, and virally spreading was one of them, and we just wanted to actually prove that this was true now, instead of just saying, yes, this could be possible, saying, no, it is possible. And what was necessary to make this happen is that we had to sort of upgrade the attack. The original attack required you booting in FreeDOS on your machine and then running a Broadcom option ROM updater that was literally a DOS exe. So no more of that. Basically, Trammell ported, there's ftool code, ETHTOOL, ftool, over on the Linux side of the world. So I put Linux on one of my Macs in order to do some experiments with other proof of concept code. Found that you could use ftool to just directly update the Broadcom Ethernet adapter option ROM, and from Linux it was literally trivial. So then Trammell ported the Linux code from the kernel driver over to Mac and made it just trivial that now we have code that runs on Mac which can update the option ROM. And so basically that looks like, you attack the system, you escalate your privileges so that now you can talk to the PCI address space, and then it's just literally the Linux code already does the hard work for you. It already knows how to talk to the magic mailboxes on the Broadcom thing, and you just write the malicious code into the option ROM. And this is just to say that it's not just these Thunderbolt Ethernet adapters. There's a bunch of other peripheral devices which have option ROMs which can potentially be updated. We just haven't looked into it at this point. So Apple's response on this is that first of all, we did all of this work, back in the spring. So OS X 10.11, even if you're root, you can't necessarily install the kernel drivers which we were using for this, and that's fine, but it's been understood since 2006 with when Joanna Rakowska was talking about is game over, right? Back when Vista was still in beta, Vista was adding kernel driver signing, right? And they said, no, you will not be able to just get into the kernel anymore on Windows because you have to have a digital signature. But of course, it's the case that any digitally signed kernel driver that has any vulnerability still allows an attacker a way into the kernel. So that's fine, but that's necessary but not sufficient. But the better response to this, the good thing to hear here, is that, again, these new iMacs are not going to load option ROMs by default. And so that's great for the new iMacs. I don't see any of the new iMacs in the crowd today, but eventually that'll be for our laptops. So we won't be able to load option ROMs by default. Do something magic, you'll be able to load them still. But yeah. All right, final thing. Exclusively for you here at Hack in the Box today, let's talk about the Queen's Gambit vulnerability and its applicability to Macs. So Corey won the pony this year for the best privilege escalation bug because the Queen's Gambit vulnerability was something he found in open source reference code that allows you to escalate from ring 3 user space code all the way up into the BIOS, right? Ring negative 2.5 as I call it. So this has affected hundreds of PC models, literally over 500 HPs alone. And so this is a very prevalent vulnerability. So this actually was talked about at Black Hat last year. So this was found in December of 2013. This was disclosed in December of 2013. This was talked about publicly in July of 2014. And then, we're more than a year after that, right? So Corey went and he looked at the open source reference implementation. And he found a variety of integer overflows, and he found them specifically on the code paths that involved BIOS updates, right? So this is UEFI secure boot. It's good. It makes it so that attacker can't just automatically overwrite your BIOS code. But you've still got some time window between when you reboot and when code is running, checks for a BIOS update. When it processes a BIOS update, it'll do some amount of parsing in order to sort of put the BIOS update back together again before it can actually check the digital signature. Without going too much into it, I don't remember whether we have slides that show it easier. No, we don't. So without going too much into it, basically, BIOS updates would tend to be fragmented across memory. So they wouldn't expect that you could just slap a BIOS update that's 16 megabytes big into physically contiguous memory. So it'll be scattered around in memory, and then the BIOS has to put it all together. Basically, there's integer overflows and your typical buffer overflow type bugs in the coalescing of the BIOS. And that means an attacker can buffer overflow, gain code execution in the context of the BIOS while the BIOS is completely unlocked and waiting to write this contents to the flash chip. So game over sort of attack. At the time, again, going back to our CERT vulnerability disclosures, we had a number of vendors that said they were vulnerable, right? And that's sort of what we would expect. And specifically, Corey wanted to say, here's the open source reference implementation code, but how do we know whether or not that actually made its way into any real shipping systems? So he went and he looked at an HP Elite book that we had laying around. And, you use hex arrays and you actually, decompile the stuff. You use the open source reference implementation code, and you can find that things sort of match up pretty well, right? You can see the number of descriptors count incrementing. You can see a descriptor buffer being incremented. So yeah, that said that on this particular Elite book, the code is definitely there. It definitely matches what we see in the open source reference implementation. So then there was the question of, again, all of these guys who say unknown didn't reply, just assume they're vulnerable. But for those who said they were not affected, this was because they would generally say, we roll our own BIOS update mechanism. We don't use the open source reference BIOS update. We've done something else there. And that's fine. We understand that. Given that response, it's like, okay, if you did something completely different, we understand, then you shouldn't be vulnerable to this, right? So, but the thing is, then when we start looking into it, right, the whole point of this exercise was take some old bugs that we've already disclosed, already been public for, years potentially, look at them on Macs specifically. So you go look at the open source reference implementation, this capsule update. It has a GUID that's associated with the file on the firmware file system. And you go look at the Mac's firmware file system and you see the exact same GUID. So these are supposed to be 128-bit numbers. There shouldn't be too much chance for collision here, right? They're supposed to be globally unique identifiers. So if we see a collision, we have, high confidence that that's probably the same code. Right? High confidence is good, but, trust but verify. So we go and we look at the HP BIOS update, the HP BIOS update code, and then we look at we look for the same sort of code in the Mac file of the same GUID, right? And we can see that these things pretty much sync up exactly the same. One's a do while loop, the other's a while loop, but 6 of one, half dozen of the other, right? So the code looks promisingly similar to suggest that this vulnerability probably exists. Then the next question is, okay, well the code's there, but is it actually reachable? It's there on the firmware file system, but is it reachable? And the answer is yes, right? So you have to say, like, what is the condition for which this code is reached? We already knew the condition from the past work. You create a magic UEFI variable called capsule update data. If you create this magic variable, capsule update data, with this data structure and this coalescing that goes on that leads to the vulnerability, if you create that and you reboot the system, then you can see that it's actually chewing on that magic variable and going to lead itself, I can't remember, never mind, lead itself to have the vulnerability. So what this means is sort of, we have this code that, according to the manufacturer, that's not invocable. Maybe it's there, maybe it's not, but they say, that's not possible to get to. So we like to call this BIOS necromancy, because we have code which the vendors are telling us is dead code. They say, that's not anything we have to worry about. We don't have that vulnerability. We rolled our own BIOS update. And it's true. They have their own BIOS update mechanism, but they also have this dead code just sitting around on the flash chip as well. So invoking malicious code for the purpose of attack, that's our BIOS necromancy fund. So this essentially means that you've got double the attack surface in these sort of situations. And I want to be clear, this is not like an Apple-specific sort of thing. We've actually seen this on other vendors in other contexts. It's sort of, the UEFI development environment leaves much to be desired. So it's a situation where you've got like this giant code base and you've got all these code files, and then you set some configuration things that say I'm going to use this code and that code and that code there. And you may or may not know exactly what code is making its way onto your actual firmware. But when you have these sort of situations where you think stuff is disabled, you've got, double the attack surface. So the mitigation for this, of course, is, know thy code, right? But unfortunately, it's not always that easy, because essentially, depending on the level of unit tests and QA type capabilities that a given vendor has for their BIOS, it's very hard to say, like, we definitely don't ever use that code in any circumstance ever, right? There's a question of, if the code's there, or if someone, was it left there accidentally? Was it left there intentionally for some particular use case that we don't know about anymore because that engineer left, something like that? We've seen with a lot of cases where the BIOS vendors don't necessarily, they can't say with definitive certainty that a particular piece of code is never meant to be invoked, right? And if you can't say that with certainty, in the BIOS world, you always play things very cautiously, right? You leave code in there, you err on the side of caution, you leave code rather than removing it. Because if you remove the code and it is meant to be invoked in some particular circumstance, that means now you potentially have a vulnerable situation where someone tries to invoke that code, the code isn't there, and the system falls over and it's bricked. So the BIOS vendors are always going to err on the side of caution and try not to, they'll leave code and then code accumulates and then you get more vulnerabilities. But, obviously this is the kind of thing where you have to get your hands around it. You have to understand what's actually there, because otherwise you can't reduce your attack surface and you just have this growing vulnerability down in the deep dark. So Apple's response to the Gambit's vulnerabilities was that King's Gambit, which is a different sort of later stage vulnerability, is not present, and we haven't actually went off and verified that. All we did is we looked for Queen's Gambit, and we said, yes, that's definitely there, and here's the proof of concept exploit to prove it. So we showed that the Queen's Gambit was there, and Apple said we've made modifications to protect against running unused functions. So hopefully, starting in OS X 10.11.1, right? I haven't had a chance to try out this developer beta yet, but hopefully that'll be out soon. Once that comes out, then we can actually check, whether or not the Queen's Gambit no longer works, and more to the point, we can find out how prevalent it was, because we don't even know at this point how many machines it actually affects. We just tested it on some systems, and we said, yep, it's definitely there in some systems, but we didn't go out and look throughout all possible systems. So, in conclusion, the dark side of the Force is a pathway to many abilities that some consider to be unnatural. Right? Furthermore, UEFI vulnerabilities are often shared between different systems. I don't care if you're an EFI system that forked off a decade ago, you still maybe have some code that's in common with the modern day thing. And the modern day thing is open source, online, where anybody can be looking for integer overflows all day, every day, right? So that's kind of a problem. Ultimately, this is sort of the breakdown of bugs that we looked at. Snorlax and Prince Harving, that was straight up patched away, right? The fact that they made it so that the lockdown bits get set by the BIOS before executing the code script, that means that went away. Darth Venomous, we call it partially patched because there still is the TSEG MB, and I can still break into SMM on Macs. That's a problem as far as I'm concerned, because SMM is the place that no one can ever look. We as defenders can never inspect system management RAM. That's a great place to be hiding, and it doesn't matter whether you do firmware forensics or memory forensics, you just can't look there. You just can't see an attacker in SMM. Speed Racer, we're calling this still vulnerable, even though I said technically they're not vulnerable because they don't even have the protection in the first place for us to need to bypass. But the basic point is Intel recommendation and our recommendation is use all of the access control bits available to you. So until SMM BWP is used, if you can defeat the protected range registers, everything falls down. I guess I put King's Gambit there. That should say Queen's Gambit. Queen's Gambit, definitely vulnerable. I'll fix that slide here shortly. And theoretically, well, not theoretically, once 10.11.1 drops as public, then that should deal with it. The Sicilian, we didn't even talk about today. That's sort of an older vulnerability where, again, it was an Intel hardware vulnerability, the cache attacks, if you're familiar with circa 2009 Invisible Things Labs and Loic Deflau's work, French researchers' work, that had to do with interactions between system management mode and caching, and Intel had to spin new hardware for that with new protection bits called system management range registers. And so there are systems, there do exist systems where, well, yeah, never mind on that. All right, and the last vulnerability is the setup vulnerability. This is a secure boot defeating vulnerability, but Apple doesn't use secure boot, so it's not applicable. And it was mostly sort of in AMI code bases that actually had that. So, the general recommendations that we always give to vendors is that, Apple or anyone else is testing old vulnerabilities against your systems, right? Just because, if someone comes out and they say, hey, there's an ASUS vulnerability over here, and they post it to full disclosure, vendors have to realize that they are not special and unique snowflakes. UEFI systems all sort of look like each other, and a vulnerability on one potentially affects the others. Silently fixing vulnerabilities, that's a no-no, right? So when you have new machines that are just not vulnerable and old machines which are still vulnerable, and it takes a researcher to go figure that out, that's not good mojo. And using all the locks, like I said, that's something we hammer on is use all the protection mechanisms available to you so that you're not just one lock away from defeat. Anyways, I don't think you're all BIOS vendors, so I'm going to skip that. What can the audience do? Obligatory Band-Aid, right? So obligatory Band-Aid is for this ThunderStrike type attack. We did release an option ROM integrity checker, so nicely all of the option ROMs for Thunderbolt Ethernet adapters, at least the ones we've seen to date, they look basically exactly the same. They're all the same binary. The only stuff that's different is like MAC address, and checksum. Right? So pretty much you know what a legitimate option ROM should look like, and we can integrity check that. So if you go to the GitHub page, you'll find that. Thunderbolt option ROM tool, that's like the open source tool in order to dump the option ROM. I have the binary version of that in our Legba core thing. Tremel was going to be releasing that, but eventually his company said that he can't, so we're going to instead. So we'll post that eventually as well. All right, the last thing, always got to be pimping, opensecuritytraining.info. If you don't already know about it, go check it. Go get some mad skills. Corey and I have put up our like x86 rootkits. Life of binaries is portable executable format and ELF format. A whole bunch of training on exploits and assembly, ARM, x86, all sorts of good stuff. Coming soon, BIOS class. And by soon, I mean Sunday. So coming soon, BIOS class. All right, and that's it. Looks like I have 3 minutes and 50 seconds for questions. Thank you for attending the talk. Thank you for voting in the talk. Take any questions.